Looked at an example last time of how we can calculate an exact area by taking the limit of this sum of rectangles as the number of rectangles goes to infinity. So this is, let's kind of just be more specific about that. So we call this a Riemann sum. Taking the limit as n approaches infinity of the sum of the area of the ith rectangle. So you remember what that looked like? What did that look like? The sum of, how did we define that area of that ith rectangle? We had to do rectangles as height times width, right? Okay, good. So we called it f of a plus I delta x. Good. Does that make sense? Okay, so that defines the right-hand edge of each rectangle. That's the easiest part to define. So there's the height times delta x. Good. Okay. Now, we're defining our delta x as being what here?
B minus A over N.
Okay, good. It's going to be, we've defined delta x as being a uniform slice here. So it's going to be if we have the width of the whole area divided by the number of rectangles, that's what defines delta x. Okay. We can be a little more general with this in calculus, although this is the way we're always going to do it. Okay, let me tell you what I mean by that. So a Riemann sum in its most general form is actually written like this. The limit of the sum of f of c sub I, where c could just be any convenient way to slice up the area under the curve. Okay, it doesn't have to be this way, but we'll always use this way, times times the width of, hang on, never mind, we gotta go back real quick. Times delta x sub I, where delta x sub I, what they're saying here is they're preserving the ability for us to have the widths of the rectangles vary. So they don't always have to be the same uniform widths. If we do that, though, we have to make sure that the widest of those intervals still shrinks, the widest rectangle still shrinks down to 0. And so there's a way in calculus of doing that. We call that the norm. It's like double absolute value bars around the delta x, and that's saying, so worst case scenario, the widest of the rectangles, even that one still has to shrink to 0 in our limit. Okay, this is way, way overkill. We don't need to do this. If we had more time, I would show you an example where our scheme of doing things by cutting areas into uniform rectangles doesn't work very well. A good example would be if we're going to add up the area under the curve, the square root of x. If you do that, uniform cuts makes the algebra really difficult. It's much easier to make progressively bigger cuts, and just make sure that even the biggest cut, you're going to shrink that one to 0 more slowly than the other ones, but it's still going to go to 0. That's super overkill. We don't need to focus on this stuff because you're about to learn a trick that supersedes all this stuff. And so I don't really care that you become experts in taking discrete Riemann sums, because you'll never do it. You're always going to just use this trick I'm about to show you anyway. When we really enter the realm of integral calculus, there are a whole slew of these standard forms and techniques we use to do integrals without adding up areas under curves, without having to do this stuff, without having to discretely break it into rectangles and take a limit. And so I'm not going to take you through those examples. If you're a math major, you'll go back and look at these at some point. But if you're not, if you're going to be an engineer, you won't. There's no need to. We're going to learn a much more practical way of approaching this. So from our perspective, here's what we're always, to make a long story short here, here's how we'll approach this in kind of a practical sense. This is the most general form of a Riemann sum. But for us, we can always just say, okay, delta x sub I, we're just going to let, instead of indexing the width of each rectangle to the number of the rectangle that we're counting, we'll just cut them uniformly. And so delta x sub I for us is always just going to degrade to delta x. Plain old delta x. We'll just choose to cut them uniformly because, of course, we always can. Right? As long as the width shrinks to 0, there's nothing that prevents us from doing that. And c sub I, think of c as being convenient. And rc sub I, the areas where we choose to calculate the heights of the rectangles, we'll always choose that to be a plus I delta x. And so everything we've done still holds. It's just one way of dealing with a very general kind of a sum. Okay? And for us then, the limit just, instead of saying as the widest interval goes to 0, well, that's going to necessarily happen if the number of intervals goes to infinity and they're all cut uniformly, right? Does that make sense? Think about the width of this delta x up here. If delta x is b minus a, some finite number, some constant number divided by n, as the number of rectangles goes to infinity, well then that fraction goes to 0, doesn't it? Right? So nothing's really changed for us. Okay, but this is the most general form. All right, so let's look at, I want to look at an example here, and we're going to do something we don't normally do in math. We're going to use some inductive reasoning. And later on we'll come back and I'll show you a more formal proof of how this works in all cases. But we're just going to see if you can notice a trend. And then that trend is going to be our shortcut. Okay, so let's take a look at a specific example. Let's look at, how about f of x equals x to the 1. I think that's what we want to do. Yeah, let's do that. Okay, and we're going to add up the area on the interval from A to B. Okay, see if we can come up with a shortcut here. So for now, we have to set this up as a Riemann sum. So what's that area going to look like? Area equals limit of what? Sum f of a plus I delta x times delta x as I goes from 1 to n in the limit that n goes to infinity, right? Now what's our a? Our a is just a, right? What's our b? It's just b. Our function is x, f of x equals x. What's delta x? Okay, so delta x we can replace with our b minus a over n. That's one substitution we can make, right? And then we can go ahead and say if f of x is x, f of junk is junk. So f of that is just going to be that, right? So we can write this as limit of sum of the quantity a plus I times b minus a over n, right? Times delta x, right? As I goes from 1 to n. Okay, now what? Distribute. Okay, we can distribute this term right here through to both parts, right? And so that's going to give us the limit of the sum of a times b minus a over n. We'll just leave it like that. It's fine. Plus b minus a quantity squared over n squared. Everybody that? times I. Okay. As I goes from 1 to n. So I'm summing up two terms. You see that? I'm summing up this term, that's term number 1, plus term number 2. What's our algebra of sums tell us? When we're adding up two sums, what do we do? Separate. Okay, we'll sum them term by term, right? So we'll split that up. So now we're taking the limit. We won't worry about the limit for now, right? We're just focusing on the stuff in here. We're working inside out, okay? So we get this first sum. Now I'm summing that as I goes from 1 to n. Are there any i's in this? No. Okay, so what's that mean? All this stuff, you're right, all this is a constant with respect to the sum, right? Because the sum is working on the i's. So what's the summation formula that goes with that? The sum of a constant is constant times n. Okay, so this part right here is just going to give us that constant, a times b minus a over n times n, right? And the n's will cancel, right? Okay, and then those will go away. Okay, plus, what about over here? Okay, I've got the sum of I times this constant, right? So good, so we'll get the, whoops. Right, we can pull that constant out front, like we do. B minus a squared over n squared times. Now, what's the sum of I?
N times n plus 1 over 2. Right there.
Okay. Right? And that's just one of our summation formulas. Okay. So let's clean that up a little bit. So here we've got a times, and we go ahead and distribute. Sure, we get. You want to do that? Yeah, why not?
AB minus a.
Okay, plus. Now what's happening over here? Okay, let's. When you're using these summation formulas, you probably come to this conclusion, but it's always a good idea to just go ahead and distribute through, right? So this is going to give us this whole part right here is just going to be n squared plus n over 2. And I've got this n squared that's going to be in the denominator, right? So I'm going to get b minus a squared times. I'll put the 2 over here, how about? But then I'm going to end up with, so that 2's, we're lumping it together with this guy. But then I've got this n squared plus n over n squared. If I reshuffle things, does that make sense?
So you get 2n.
Yeah, so I'm going to go to the next page. We're in another room. Okay, good. So yeah, so then we end up with the limit as n approaches infinity of a b minus a squared plus b minus a squared over n squared. Oh, sorry, over 2. Times 1 plus 1 over n. Okay, now what? Okay, we could distribute. We could. Don't really need to though. take the limit. Yeah. If I take the limit as n goes to infinity, well, there are no n's with any of these first two terms, right? So nothing's going to happen to them. But there's only one n in here. What's going to happen to that term with the 1 over n term? That's going to shrink to 0 in our limit, right? And so we end up with the answer, ab minus a squared plus b minus a squared over 2, right? Okay, so there's some algebra to be done here, and we got to just kind of reshuffle things. We're going to see if we can make this look like something a little simpler than that. So what if we expand out the b minus a squared part? So I get ab minus a squared plus, if we expand this out, that's going to give us what? B squared minus 2ba plus a squared all over 2. Right? Okay, what if we get a common denominator? So we can add up all these terms. What do I have to do to these other terms over here? 2. Okay. Okay, so we're going to get common denominator of 2, and then that's going to give us 2ab minus 2a squared plus b squared minus 2ab plus a squared all over 2. Okay, so we get some cancellation, don't we? Okay, so we get that 2ab canceling with that. I get a squared minus 2a squared. So negative a squared. Okay. And so my final answer ends up looking something like this. B squared minus a squared over 2. Okay. Right? We could even write that if we wanted to as b squared over 2 minus a squared over 2. Okay? Now think what the original problem was here. We've got to kind of look back a little bit. The original problem was the area under the curve x, right? The area under f of x equals x on the interval from a to b. Okay, there's kind of a math shortcut here that are some notational stuff I'm going to introduce. This notation makes a lot more sense once you know the trick. But for now, just see if you can understand the relationship. So really what I've got here, I've got the same term. I've got a b squared over 2 minus an a squared over 2. So that's just some expression in the form, say, x squared over 2, where x could be either b or a, right? So we could write this if we wanted to as something like this, x squared over 2 evaluated from a to b. What that means in math is I'm going to plug the b in first, minus, then I plug the a in. Okay? Does that expression right there, x squared over 2, can you see a relationship based on the stuff that we've just learned in chapter 4? Can you see a relationship between that and x? It's the antiderivative, isn't it? How about that? Right? Weird. It's the antiderivative. And so this brings us to, which time do we got? A little bit of time. This brings us to, you got it, that's what it is. We can demonstrate this again with another example, but the shortcut is that the area under a curve is equal to, area under f of x from a to b is equal to the antiderivative of f of x, right, evaluated from A to B. Okay. And the answer then we always take to be, if f is the original function and capital F is the antiderivative, whatever that might be. In this case, f of x was x. Capital F of x, the antiderivative, was x squared over 2. Right? We just evaluate that antiderivative over the interval a to b. That's what's called the first fundamental theorem of calculus, and that is a great trick. That makes life much, much easier for you, doesn't it? Right? Now let's look at an example or two of this so you can see just how this works and how simple it is. So given that trick, let's find the area under, let's say, f of x equals x squared on the interval from -1 to 4. Okay? So that's just going to be this new kind of antiderivative. Now the name for this, by the way, is called a definite integral. We don't call it an antiderivative anymore. An antiderivative just means the function whose derivative is the integrand. But a definite integral is different. A definite integral means that now we're actually looking for a number answer, looking for an area under a curve. There's a definite answer to this. A lot of times when we talk about an indefinite integral or an antiderivative, they mean the same thing. Whoops, can't spell. Antiderivative is exactly equal to what we call an indefinite integral. Okay, in fact, we'll start calling it an indefinite integral. That's really a better calculus term for it. Indefinite because it's got that c in the answer, right? But when we did an antiderivative, we got back a whole family of curves. Like, for example, we would have said that the antiderivative of x dx is what?
X to n plus 1.
Okay, so in this case, n is 1, so it would have been x squared over 2 plus c. Right? It's indefinite because we've got that constant attached to it. Okay, but when we're trying to find an area under a curve, that becomes a definite integral because now we're going to evaluate that over known limits of integration, what we call them. Okay? And so this goes from an indefinite integral to a definite integral. So definite integral equals area. So let's set this one up then. The area under f of x equals x squared on the interval from -1 to 4 would be what definite integral? So we set it up as an integral. There's my integral sign. What's the integrand? X squared. So there's the function that's inside the integral, but I got to put a dx there, right? Now here's the part that's a little different. It's a definite integral, which means that the limits of integration, meaning the area, the values that bound the area we're adding up. The lower limit always goes on the bottom. So we're going from -1 up to 4, and that means an area. That means we're adding an area, adding up an area under that curve from x equals -1 to x equals +4. That's how we will from now on interpret that definite integral. Okay? But the calculus part stays the same. Right? What is the antiderivative or the indefinite integral of x squared? Okay, so we're going to get x cubed over 3, but we're going to evaluate that from -1 to 4, right? And so what that means to us from now on is it equals the upper limit, the function evaluated at the upper limit minus the function evaluated at the lower limit. Okay. So it's going to look like 4 cubed over 3 minus -1 cubed over 3. And that's our exact answer. Got that?
This is only for inscribe.
This is, well, no, it doesn't matter, because think about what this process encompassed. This process relied on our taking a limit as n went to infinity. And so it makes no difference if we use inscribed or circumscribed or trapezoids or whatever, because the area is going to be exact. When the number of intervals goes to infinity, the area under the curve is matched up perfectly. So we don't have to mess, you can breathe a huge sigh of relief. You don't have to mess with any of that inscribed, left edge, right edge, all that stuff just goes away. We've now got this shortcut that gives us an exact area much, much more easily. Okay? Make sense? Okay, and so if we look at the way this is written, and I want to just pay attention to this, the first fundamental theorem just says then that the area given to us by a Riemann sum can much more easily be written as a definite integral. Which just equals the antiderivative evaluated from A to B, which you can also think of as being this if you want to. The antiderivative evaluated at B minus the antiderivative evaluated at A. Voila, the trick. That's what we call the first fundamental theorem. Let's try one more of those. Just make sure you guys get it. So let's try. And that's all in the book. It's not like that's anything so mysterious. Let's try about trigon. Okay, so what's that asking us to find there? What's that mean in terms of the graph? Area under the curve 1 plus sine x, okay, on the interval, yeah, where x runs from 0 up to pi. That's the part where we want that area, right? Okay. So, what's the antiderivative of 1 plus sine x? What's the antiderivative of 1 dx? X minus cosine. Good. Okay. Evaluated from 0 to pi. Okay, here's where you can make a choice. And really, this doesn't matter, whichever way you want to do it. I personally have a little preference here, but it's totally up to you. I could, if I want to, I can just evaluate this whole thing at pi, so I can do this. Pi minus cosine pi minus this whole thing evaluated at 0. That's fine to do. Or, if I want to, I can split this up into two separate terms. I can think of this as being x. I can evaluate x on the interval from 0 to pi minus cosine x on that interval? Doesn't matter, it just depends how you're gonna shuffle up the terms, right? If I do this way, it's just gonna look like pi minus 0 minus cosine pi minus cosine 0. Same math, isn't it? Right? I kind of prefer to do it this way, the blue way. I like to split these up into individual, each of the terms in my answer. I like to evaluate those separately, but it's just a matter of preference. What's our answer going to be? Let's go over this a little neater. We'll go and do it over here. So what's cosine pi? -1. Okay, so this is going to give me pi minus -1 minus 0. What's cosine of 0? 1. So minus 1 would be +1. You buy that? So my final answer is just pi plus 2. Is the exact area under that curve. Amazing stuff, huh? Okay. We're gonna wrap some things up, but to me, it's a lot easier to wrap this stuff up and to get, to kind of put the finishing touches on the theory part if you know how to do it well. And so what I'm gonna give you some time now that you've got the trick. I'm going to put the assignments up. 4.3 is a pretty short one. 4.3 is just a little continuation of 4.2. Now I don't want to spend, I might even shorten that up. I don't want to spend a ton of time with you guys doing all this Riemann stuff up, these discrete sums, because it does take time. And I really want to be able to push a little further on in the class. So I'm going to, we'll finish up the 4.2. 4.3 will be very short. 4.4 is where you get to start doing the trick. Okay, so 4.4 is where you get to start actually using calculus to take integrals instead of using limits and sums. And then, once we get through that stuff, we'll kind of come back and put some finishing touches on some of the theory involved, and then we'll move on to finish up chapter 4.
To the front office, please.